All right, so welcome everyone. Good morning. Welcome to our last session in this year, our pre-Christmas session. My objective today also is to discuss with you the last chapter, I would argue, in our course that is of immediate relevance, let's say, to the assignment. Feature engineering and selection, that's the topic for today. And with this topic being covered, if we think backward, we have revisited data preparation, and data transformation pretty much is what's on today's agenda. And you clearly have seen a lot in terms of how to build predictive models. And this is exactly what you are required to do. These are exactly the skills that you need to demonstrate in the Kaggle assignment. So with today, you really have all you need, and then with today's tutorials, you also have the code examples attached to these skills, and that should ready you for the assignment. So, well, naturally, I want to talk about these two separate tasks, engineering and selection, and give you some advice how you can approach these tasks. That's pretty much the core of this session. So, quick recap as usual. We have our analytical pipeline, our data analytics process model with its individual steps, and in the past week we have spent quite a lot of time on the actual learning or data analytics step, the machine learning step here, labeled as analyze data. And now we take one step back to transforming the data. Now that you know what type of algorithms exist for the type of data we use here, for the structured tabular type of data. Now that you've seen gradient boosting and random forest and logistic regression as our workhorse model, we can take one step backward and ask, how can we organize our data such that these learning algorithms face an easier task? That's pretty much the scope of this session. And we start with feature engineering, crafting features. Remember, features equal to variables, covariates, attributes, these columns in our data table. That's what we talk about. So how can we craft powerful features? That's essentially what feature engineering is about. I consulted Wikipedia for their opinion and found this definition. It's as a process of using domain knowledge, I like this perspective, of the data, or let's say the application setting that has generated the data in the first place. Domain knowledge of the data to create features that make machine learning algorithms work. Okay, well, a tree-based algorithm should work pretty much out of the box. Whether it works good or not, entirely different question. But if you have a data set and you have a label, it should be quite possible to throw some tree algorithm on the data set and get a result. But of course we want algorithms to work well. We want good classifications, good predictions. And then we need feature engineering, fundamental to the application of machine learning, and is both difficult and expensive. It's expensive because it's often manual, and it's difficult because you need expertise. Expertise is always cost, right? It's an informal topic. They then continue after some wordy part that doesn't really matter, but it's considered essential in applied machine learning. Yeah, I would sign that. In industry, ideally you have both. You know the data, but more broadly, you know the domain. You know your business setting. If you work as a machine learner in credit risk, then you know the credit business. You have an idea about finance. You know the domain. And that enables you to craft good features. And of course, you also know all the machine learning bits, how to do R and Python, and how to do gradient boosting, and all these types of things that you know as well. But if you purely excel in machine learning and have little information about the domain in which you work, you can do okay, but you can't be super good, let's say. And the reason for that is that you typically lack the insight into the domain to come up with good ideas how to craft features. That's the reason. Because how gradient boosting works or how random forest works, it's always the same, no matter whether you work in finance or in marketing or in medicine or in computer vision. It's always the same algorithm. That's entirely generic. Feature engineering is a task where you need domain knowledge. Trying to craft better variables. And more recently, there is a big fuss about deep learning. And if you read up on deep learning a little bit, one of the promises that you will come across of the big statements here is that the beauty of deep learning lies in these deep machine learning methods learning features automatically. So they sort of automatically take care about feature engineering. Well, long story short, that does work with textual data and image data, but there is rather little evidence that it works with structured tabular data. In the identification step, indeed, you basically, or the notion of the identification step would be that you pull together as many data as you can get access to. You're trying to make X as large as possible while sustaining some belief that whatever X, whatever feature you pull together will be correlated with Y somehow. Or else you just pull together all the data and count on your ability to do feature selection to see and to check which of the features that you collect are correlated with Y. And then the feature engineering would be to improve X, to improve this correlation in order to simplify your task. And naively, we could believe that a smart algorithm is able to do that for us, but in my opinion, this view is a little bit naive, and you will be able to see, even with the tutorial data, how features that embody a slight bit of domain expertise will help you to do better. In fact, one example is coming right now, although this example is a little bit mechanical, but I pulled that from a nice post in KD Nuggets, where the authors also make the case for feature engineering. And their motivating example, introductory example, is to come up with a situation of the data that is described as or that looks like, as shown here on the left-hand side. We do observe a clear pattern between classes and our two features, and we observe that this pattern is nonlinear, which means that any linear model that we might use and apply to this data would fail. And then if you perform a simple transformation of your data, if you move from the Cartesian coordinate system to the polar coordinate system, so just translate x1 and x2 into their corresponding polar coordinates, which is a very well-known high school-like transformation, then you actually obtain a set of features that allows you to linearly separate your data. So you make your task a lot easier by just applying this transformation. And then you can say, well, okay, nice, I accept that, but isn't the example stylized? And yes, it is. It is very much stylized. In the industry, we would have so many features that we have no idea what the picture would look like in these hundreds or maybe even thousands dimensions in which we operate. But coming back to our previous discussion on interpretability, there are good reasons why you might want to use a simple model. in certain applications. And if simple models fail when there are nonlinearities in your data, feature engineering can help to capture this non-linearity in the features so that linear models work again. This way, we might be able to find a healthy balance between a model that is simple, for example linear, and predictive power. If we have powerful feature, even a linear model can predict with high accuracy. And in fact, we already have seen a couple of standard transformations in chapter 4. Let's revisit these. Chapter 4 was on basic data prep. And in this chapter, we talked about outliers. And in the scope of outliers, we sort of established that if you have regression type of models, logit, but also neural networks, then outliers will impact your model and you should correct at least extreme outliers in some way, but you should do something about them. Trees are not vulnerable toward outliers. For trees, you don't have to bother with outliers, but for other models, you do have to bother about outliers. You have to take action, and action could be to truncate extreme values to some threshold. And we have discussed possible thresholds. And this is already a transformation of the features if you truncate the outliers. Or we discussed the normalization of features. Again, trees don't care. For algorithms that work on the basis of distance calculations, normalization of the features make a lot of sense. I would say it's close to mandatory. And if I normalize a variable, if I project all my income values into the range +1 to -1, that is a transformation. Same with discretizing numerical variables or regrouping discrete variables, where we talked about binning approaches and how we can use decision trees. Some more of that later in this chapter. That also is a feature. That also is a transformation that you can classify as feature engineering or weight of evidence. Same story. So you already have seen a lot. And indeed, considering these examples, there is not much domain knowledge involved. These are more standard steps that you can consider in the data preprocessing pipeline in order to improve your model. And even a powerful deep neural network model will be vulnerable toward outliers, so curing or addressing outliers will help you do a little bit better. Let's try to identify. Feature engineering, if you really consider it in a narrow sense, if you try to bring in domain knowledge, it is obviously dependent on the domain in which you work. So it's a bit difficult to discuss in courses like this one, because it's so domain dependent. My aim is not to ready you for various domains. To be really honest, I lack the expertise in most domains that exist. There are maybe a handful or less that I know a little bit about. Credit risk being one of them, maybe marketing the other. But then, what do I know about medical applications? Very, very little. So, but let's try to identify some meta approaches. One transformation that you see very often is to construct ratio type of variables. And this is in a healthcare type of example. If you want to make a model, craft a model that scores the vulnerability of patients to certain type of illnesses, certain clinical tests or measurements like this one, weight, height could come into play, and then you could work out something like the body mass index in order to condense the informational content in weight and height into one predictive feature. You just form a ratio of two variables that relate to one another. And the picture is meant to signal how this can make your life easier. And if you think about business applications like credit risk also, that makes so much sense. If you want to predict whether somebody is going to default on a loan, obviously the amount of credit you would expect has an influence. If I lend more, then my risk to default also is more, because maybe I just become unable to repay all this debt. But on the other hand, clearly this also depends on my ability to repay, i.e. my salary, my income. So income also is a variable that would come to mind. And then if we continue this line of reasoning, obviously these two variables, both of which we believe to determine credit risk, income and credit amount, relate to one another. So something like debt to income ratio is a feature that you would find in any bank scorecard used in industry. Or when we talk about mortgages, then loan to value. What is the value of the collateral, say the real estate that you're trying to purchase or that you're purchasing with your mortgage? What's the amount of the mortgage? This is another very popular variable that comes up in any credit scoring model that refers to mortgages, where you have collateral to secure the mortgage. So ratio variables are something to consider. That's something that's sort of generic. You can think about meaningful ratios in numerous applications. Same if you predict corporate failure, corporate insolvency. You would typically consider ratios of balance sheet information. What else? In a similar direction, you might have measurements that are recurrent. Examples would be something like the account balance. In a credit risk example, if you have a customer that has some credit but also has a checking account, the account balance changes daily. So you have many different observations for the account balance. Also, the bureau score, your Schufa score, changes over time. Probably not daily, but maybe quarterly. Or, well, with Schufa, anytime new information becomes available to them, they will update your score. These are examples of measurements that are temporal or that change over time. And whenever you use such measurements in a model, the question is, which version do you use? If I predict your credit worthiness based on the Schufa score, do I use the most recent version of your score? Probably yes. But would it maybe make sense to also look in the trajectory of your score? Maybe your score is relatively low compared to the average population. But maybe this score compared to your previous one is much higher than before. So the trajectory indicates that you're on a very, very good path to becoming more credit worthy, let's say. This trajectory would be important, but I can only include such information in my model if I use multiple versions of your credit score or the development of your checking account, right? It's more general. Whenever you have repeated measurements of a variable, the question arises which version to use in your model. Very often you can make an argument that there is no single best version and that multiple measurements somewhat might be useful. So what's done in practice quite often is to calculate features by means of aggregation. You're just aggregating over all the measurements of your bureau score or over all the measurements of the account balance that you have access to. And there are many ways how to do that. Aggregating means just applying some aggregation functions, the sum, the mean, the min or the max. You can look at some quartile or percentile of the distribution. You can even aggregate by calculating something like a moving average or maybe a recency weighted moving average. There are many ways to do that. But this development of trend type variables is something that is done a lot in feature engineering and is again sort of generic and is making sense in many different domains. So also have that on your list. Ratio variables, trend variables are the type of features that you would want to have on your list when getting a data set, trying to think yourself into the problem and trying to identify possibilities for crafting good features. There are also certain transformations. The focus here is more on an individual variable where you have this variable, say income, you examine the distribution of the variable and you detect that it's non-normal, has some type of strange, weird distribution, skewed to the left or to the right, normally to the left, as you see in the upper example. So this one here that is a distribution that is quite representative for many real-world variables. Count variables in particular, but also variables like income, credit amount, spendings, etc. Then again, definitely linear models, but linear models may even require normality. It might be an assumption of certain models, but in general, having the distribution of your feature values more normal is often found beneficial. I don't dare to formulate that in a less soft manner because the problem is most severe, again, in the scope of linear type of models, but never forget these models are very popular in the industry. So it makes a lot of sense to think about linear models. And the question arises, can we make our variable look a bit more normal? And yes, we can. There are certain transformations. If you have a count variable that is strictly positive, and you observe this left skewed tendency, just consider the log of the variable. The distribution will look more normal if you calculate the log of the variable. And you often heard, I bet, about log linear models. As a matter of fact, this is a very common transformation considered in econometrics, also in marketing, where you realize the effect of an independent variable on some dependent to be nonlinear, and then you fit a linear model to the log of that variable in order to take account of that. So that can be applied. And there are more comprehensive transformations, such as the one proposed by Box and Cox or Geo and Johnson. Well, the key goal always is to make the feature distribution more normal. Secondary goal could also be to stabilize the variance that you observe if you basically sample the feature distribution multiple times. And these transformations that you see, the logarithmic one, Box-Cox, but also Geo-Johnson, commonly appear. I borrowed these graphs from a very nice blog that introduces a package called Best Normalize, a nice R package that wraps up these feature transformation plus some others and provides functionality to empirically test for a given feature or a set of features what might be the best transformation. And you see these graphs, I highlighted two of them, which depict the distribution of the features shown above. This odd type of bimodal distribution I'm trying to sketch here is something that you also observe very often when you model losses, credit losses in particular, because if you think about it, if a customer runs into default, that means the customer has failed to repay a debt. Maybe is late more than 90 days meeting a paying obligation, repaying the monthly fee. So then there is a default. And then the question is, okay, what's the loss to the bank? Well, there might be a reason why the customer was late, defaulted, and very often there will be a cure. Everything goes back to normal. And then the loss is actually zero or close to zero. Very often also things go really bad. The customer defaulted and, well, he lost his job, no ability to repay anything, so the full outstanding amount is lost equal to 100%. These settings explain the peaks at 0 and 1, and then, well, for all the other cases, the losses might follow something like a uniform distribution. And there is much research that tries to model these type of distributions using complicated nonlinear models, neural networks, but also tree-type algorithms, and well, interestingly, they all fail, which is weird. It's hard to conceptually reason why a tree would not be able to fit this data. In empirical studies, however, you observe them to fail regularly. So transformation to, well, do something about these extremely odd feature distributions often are valuable and help the algorithms, although it's not always fully understood how this works. Because indeed, a nonlinear model should be able to model this with perfection, but you must remember that the signal in your X might be rather low in many real-world cases in business. And then if we're trying to improve the distributional shape of our features a little bit, that can prove beneficial. Now, many of these features, all of the more advanced transformation here depend on a parameter denoted by lambda, which raises the question how to set lambda, and typically this is done by trial and error. Or packages like best normalize already implement the routines to do so you can fit lambda in such a way that you, well, let's say, optimize the AIC of a univariate regression model using the single feature that you focus on and your target. That could be considered as an approach to set the lambda parameter in these transformations. So it's a mini model selection task in its own right. There are other data-driven regimes. This one is proposed in a report paper by Niculescu and co-workers. They won a prestigious data mining competition in 2009, churn modeling competition using data from Orange, KDD Cup 2009. They won that one, and then we're elaborating how they won that one. And they created many features using decision trees. This illustrates the univariate setting where we have H as a feature, and they would fit a shallow tree to H, and then use the tree representation of H as a new feature, as an additional feature, in fact. So this exemplary tree would categorize H in 3 groups, and then you could add one feature, H group, which has values group 1, group 2, and group 3, depending in which leaf node the original H class ended up. As a matter of fact, this is exactly what we discussed in the data preparation lecture as a way to discretize your data. You can fit a tree to the data, which would internally use something like information gain or maybe chi-square in order to find groups. And then you just use this optimal grouping in order to discretize those features. Niculescu and colleagues, however, took it a bit further and also considered pairs of features, and in fact they also considered triples of features, to which they would fit a tree, which would then aggregate the information within these features into a new feature. A tree models interaction among features by design. This bivariate tree models an interaction between age and amount. So constructing these tree-based features is a way to capture possible interactions in the data. This approach I've never seen in practice. Well, as a way to categorize, yes, but this bivariate or using triples of variables, fitting a tree to them, adding these features, that is something that I've seen only in the scope of competitions, where you really want to squeeze out the maximum amount of accuracy to win this competition that you are participating in. Then it can be considered, so you could consider it for the assignment. It's not something that you will likely see in industry, though. You maybe have also heard about ways to extract features using methods like principal component analysis, PCA. These projection methods have been developed in a different stream of literature or streams of literature. I'm trying to summarize the overall idea in this picture, where you have two variables, x1 and x2, and where you observe a correlation between x1 and x2, and where in orange I'm trying to depict a change of your coordinate system, a little bit like moving from Cartesian to polar coordinates. That was the motivating example in the beginning. And by performing this manipulation of your coordinate system, you can come up with new coordinates, and I labeled these PC1 and PC2, the principal components. And these principal components capture, if you think about it, the majority of the variance. Specifically PC1, the way it goes right through the data, captures most of the variance that we see. It would be the dimension along which we observe most of the variance in our data. And PC2 is the dimension along which we observe the second largest variance in our data. And both PC1 and PC2 would be a linear function of the original coordinates, x1 and x2. It's a linear combination. PCA finds these optimal linear combinations. And if you use this for feature engineering, you would typically use it in the scope of engineering plus selection. You would build a model on the top k principal components, hoping that you have less variables, so it relates to our next chapter, variable selection, and hoping that among these fewer variables you retain most of the variation that exists in your data. Interesting. There are some deep learning architectures that use something like this as a building block, something like a nonlinear PCA as a building block. Autoencoders, for example, use that principle. The main application, however, is to reduce the number of dimensions for visualization purpose, or more generally descriptive analytics. Because if you think about it, these PCA1 and PCA2, we could fit a model using these two features, and likely it would do better than using x1 and x2, but it would be hard to interpret what PC1 and PC2 is, because it's a linear combination of x1 and x2. So what really is this? What is PC1? What is it measuring by linearly combining x1 and x2? So there is a loss of interpretability if we apply techniques like that. And this is the reason why it's not often used in industry, at least not in the applications I would be involved with, as a way to engineer feature. If we engineer a feature, we look for something like that, but manually, in such a way that we can justify the combination, as in a ratio variable. A ratio variable I can justify. Debt matters, income matters, but what really matters is debt to income. That is not a linear, but a nonlinear aggregation of two features, but I can justify it. Whereas what an algorithm like PCA extract is harder to justify, and this is one of the obstacles. Do you lose information or not? Yeah. Obviously, it depends a little bit on what you define as information. Information is easily misunderstood, right? Considering this example, if information is the variation of some dependent variable, we don't lose very much here because the features are so nicely correlated that PC1 alone would suffice to pick up all the variation. If that is my understanding of information, variation, I don't lose any of it if I consider all the principal components. But you're right, normally I don't. The point of PCA is not to sustain all the principal components. I want to shrink them. And then the objective of PCA is to minimize the amount of information loss by shrinking. And indeed, you might be able to get rid of numerous dimensions without losing any noticeable degree, again, of variation. But if information is understanding how X relates to Y, remember that we don't need any Y for PCA to work. PCA by itself is an unsupervised method. You can just process your data in order to maybe project it to two dimensions to depict it. But if you start from 10 or more dimensions and cook everything down to 2, unless most of the variables that you have are irrelevant, you would lose some information by projecting everything to a two-dimensional space for sure. The minimum amount, given that you reduce things to 2 dimensions. But of course, you do lose some amount of information.
You were saying earlier that
the point why it's rarely used is that once we have our final model, we typically want to interpret it somehow, and then the principal component is harder to interpret than the original features, which makes sense to decision makers. Principal components don't make sense to decision makers typically, and then we need additional techniques to interpret them. So things get a little bit more complicated. And if my goal is feature selection, then there are simpler ways to do it. I just want to mention them to make sure you have an idea of what this is about and how it relates to feature engineering, although it's not a very common technique to carry out feature engineering. But it's somewhat related, so it's good to have an idea. Summing up, looking only at the examples we discussed, it is very easy for you to create many new variables. Calculating aggregates, for example, you can look at the mean, the median, Q1, Q3, 95% percentile, whatever, and add features to your data corresponding to applying each of these aggregation functions. Or if you use this tree-type approach of Niculescu, if you consider pairs of features, there are numerous pairs that you can consider, not to mention about triples. You can really blow up the dimensionality of your data, and very often this is done because it is hard to tell which engineered feature is the best, and then you need feature selection. The examples that I discussed are not really domain driven, to be really honest. but I told you that can't really work in a lecture on data science. If you make a lecture on credit risk only, then we can discuss standard approaches in the credit risk literature, but these would not generalize to other settings. So I want to keep the focus a bit broader than that. And the techniques we see can help you to manually craft features, provided that you understand the domain a little bit over, understand the data. And very often then you need feature selection afterwards in order to filter out those features that work well from the many others that you may have created in the scope of feature engineering without the features being particularly relevant. So selection is really about reducing the number of dimensions. We typically have a lot of data. We have many raw features in many dimensions because we know so much about our customers. And in addition, if we then use the feature transformation, we can blow up the dimensionality further, a lot further. So we want to reduce the number of inputs to our model. And there are many reasons why we want that. It is generally argued that models with fewer inputs, parsimonious model, it's a nice term, right? It's a model with few features, are easier to interpret. We could discuss that and debate that, but it's fairly general statement or belief. What is clearly the case, the more features you use in your model, the more cost you'll face, because you need to gather this data for the feature and you need to store the data, and this entails a cost. Cost reduction is thus an argument for feature selection. You might improve predictive performance. You might. Many modern algorithms, if you use them right, they are not vulnerable, or at least not really vulnerable toward relevant, irrelevant, or correlated or redundant features. Runtime is a valid constraint. Certain algorithms would just take longer to run if you have many features and would need less time if you reduce features. Predictive performance, you might gain a little bit, but with many modern algorithms, that's not the key motivation. Seminal paper was by Guillon and Elisef. Isabelle Guillon, by the way, was one of the key players among the support vector machine literature. She co-authored the seminal papers on SVM. And she provides a nice explanation why you care about feature selection and what are the different routes that you can take. One of the problems is that there are so many options. The tree indicates that. If you just consider 4 variables, x1, 2, 3, and 4, you will have that many different candidate set of features, starting from the empty model, going all the way to the model which uses all 4 variables and various states in between. So you have 2 to the power of n alternative models, or -1 if we do not count the empty model as an alternative. And with any reasonable number of n, this will grow far too large to consider all possible alternatives and try them out. So a fully enumerative approach fails because it's a combinatorial problem. The number of options grows exponentially. We need heuristics that help us to navigate these many options and find good feature subsets quickly. You already see some algorithmic strategies here, stage-wise selection methods that you might know from regression analysis. There are a class of nature-inspired optimization routines that I label as evolutionary algorithms, so mimicking the principles of the Darwinian evolution, that have gained some popularity here as a way to navigate this space of alternatives. We'll look into some strategies. Before that, I would like to delineate some aspects I believe to be relevant. We try to reduce features for various reasons. To reduce cost, speed up models, maybe gain some accuracy, maybe raise the interpretability of our model. Many reasons for feature selection, but we should distinguish between features that we kick out for being irrelevant as opposed to redundant. Whenever there is correlation, then a feature can be relevant but redundant. If I have a feature for customers that captures the years of education somebody spent at high school and university, etc., and I have another feature, income, me being me would assume that there is very strong correlation between the two, because I believe in the value of education and spending years at high school and universities. So even though years of education might be correlated with whatever we try to predict, possibly the feature is redundant and we don't need it because we have income. And in order to identify pairwise correlation, you would just use correlation coefficient, produce these graphs that you have seen many times, I would imagine, that help you even in a fairly large dimensional space to identify features that are pairwise correlated, that are correlated with one another, which could then be informative for feature transformation. For example, didn't mention that earlier, if you have two correlated features, you could use one feature and the difference between the two features as two variables in your model. That should work better than using the two features in their raw form, if they are correlated. Try to extract the residual information by forming the difference. A nastier challenge would be interaction. In this example, in this toy example, the two features interact with one another. You really need both to solve the classification problem. If you have access to only one of the features, you are doomed. And the reason why this is a bigger problem is that many techniques that we use in feature selection work in a univariate manner. They check one feature at a time. And if you check one feature at a time, you cannot detect interaction by definition. So applying some univariate method that checks is x1 relevant, is x2 relevant, would find both x1 and x2 to be irrelevant. Because the distribution it sees, let's say this is only x1 and this is only x2, just making sure you can make sense of these charts, our univariate feature evaluation method would judge both irrelevant because they don't discriminate the blue, me turning colorblind, the red from the greens. Alright, let's come to the techniques. Another seminal paper, sorry for bothering you with seemingly old literature, but some papers are just seminal in their field or cultivated the very field. So although old, nice read by Kohavi and John, they basically were the first to distinguish feature selection techniques into filters and wrappers, where we should also consider embedded approaches which are sort of a mixture between the two. But let's start with the simpler case, wrappers and filters. Wrappers wrap up the prediction model or the learning algorithm. They use the learning algorithm to select features. In a nutshell, that's powerful but costly in terms of runtime. Filters are the opposite. They don't use the learning algorithm. They use something else, typically some statistic like correlation, something that's fast to compute, that is univariate, but not as accurate. And then you want to use both and integrate them in a purposeful manner. more on that soon. With regard to time, I'll skip over all these measures. Many of them you know and or have seen in previous chapters. A filter method checks one feature at a time and examines the strength of the association of the feature and the target. And then, dear goodness, it depends on whether the feature is a category or a real value, and whether your target is a category or a real value. It depends on this scaling level how you can compute association. If both are real numbers, Pearson correlation is what you want to use. Very simple. If one is a categorical variable, Pearson correlation does not make much sense. But maybe you could use something like the Fisher score, or something like Kramer's V, which is just based on chi-square analysis. I invite you to go through the coming slides where you would find some more information on each of these statistics and how they are computed. Correlation, chi-square, with a little working example, how Kramer's V follows from that, the Fisher score, the information value that we have seen before in the scope of the weight of evidence approach. And all of these measures are univariate, give you a single number that tells you feature X is this strongly correlated with target Y. Every of these approaches is relatively simple and fast to calculate. Every of these approaches is univariate and thus suffers from the potential problem of interaction. Let's come to the wrapper type of approaches. I should ready myself for stopping the unwanted animation that PowerPoint is suggesting for this session. There we go. In regression analysis, you might have seen stage-wise approaches where the p-value of a variable is used to judge whether the variable has a significant effect on the target. In standard linear regression analysis, you compare the estimated coefficient value together with its standard error to the t-statistic. In logistic regression, you can show that your test statistic is chi-square distributed. In each of the cases, you can estimate the probability of the variable coefficient being different from 0 and then judge on significance by, well, comparing your estimated coefficient to its theoretical distribution. And then you can use this p-value to carry out feature selection in a stage-wise manner. Before looking into the approaches, just note that the test statistic is always calculated in sample, which is okay in regression analysis because regression analysis typically is linear, and therefore the risk to overfit the training data is not so substantial. Well, sorry, one step back. One way to do that is you start with one variable and then incrementally add variables one at a time. Whenever they are significant, they remain in the model. If they are found insignificant, they don't enter the model. Or you start with a full model and iteratively reduce variables. These are the stage-wise approaches: forward selection, backward elimination. And what's maybe underappreciated or sometimes not discussed in depth is how do you actually select which variable you allow to enter a model, because the order does matter. When a variable enters a regression model and you calculate its significance, it depends what other variables have already entered the model. So the order of the variables matters. For that reason, I'm presenting you a little pseudocode here of an approach called backward regression trimming. The pseudocode is meant to give you at least one really workable code-like example how these stage-wise regression can be put into practice, because you need to be clear on the order in which you treat your variables. Well, with regard to time, I will not elaborate on that, but you can read up on that. And if you read up on that, just make sure you realize how computationally demanding this approach is and how many models you actually build. Less features, you save cost. Less features, you save time. Both is nice. Again, predictive performance, if you work with easy to interpret linear models, you must do that to raise accuracy, because these models have problems with multicollinearity. So then again, it becomes a cruciality, especially if you artificially create multicollinearity by your feature engineering approaches, different trend variables, for example, right? So yeah, runtime is one, but it's not the only one. And well, maybe this is where you are coming from. These selection strategies can be extremely costly in terms of runtime. The idea would be that you routinely update your model every now and then, but you don't decide on the features every time. So you do that far less often, and then overall you still improve. So it's different types of runtime that you consider. And there are quicker ways to do that. If you think about it, and we will have a tutorial on that as well, here you really take out one variable from a full model, and in each stage you try to single out the one variable that is the least important one. And this makes it so complicated. This is why you need to build so many models in this framework, in the backward regression trimming. Much quicker heuristic would be you rank your features in the order of importance using correlation or some other filter, and then you allow your features to enter your regression model in that order. It's a heuristic. You don't think about interactions. It's a heuristic. Its magnitude's quicker. So you can basically vary the way you put that into predictive. Filters versus wrappers. The one is quicker, but less accurate. The other uses the prediction model, i.e. stage-wise regression. This makes it a lot slower to carry out. But if you put the features in a model and check how the model performs, you get some insight into how features work when put in a model together. So to some degree, you are robust toward this problem of features that work with one another. And you assess features in a multivariate manner. This is why it's typically better, more accurate. My suggestion, what works well in practice, is you use both. If you have many features, you first kick out the very long tail, the noise, using a filter, and then once you obtained a more manageable set of features, you use a wrapper type of approach. The bar plot is meant to show you a reasonably representative distribution of feature importance score. Imagine the values that you see here to depict the correlation between a feature and the target. With real-world data, you would often observe something like single features or a small set of features being really relevant, then a gray zone where features are somewhat relevant, and a long tail of features with seemingly low importance. I've seen that many times with real-world data, and you will also see that if you check the home credit data set. So it's quite representative, I believe, especially if you have high-dimensional data. And then you might have too many variables to try a wrapper approach like backward regression trimming from start. And a simple filter might enable you to, there is no theory where you put the threshold. but it should typically allow you to discard a sizable number of features and then focus your attention to whatever remains. And the set of what remains could be as large as you have resources available to carry out a more elaborate feature selection strategy, such as a wrapper-based approach, such as backward regression trimming. Where, by the way, you're not constrained to use p-values as your guidance. You could always also monitor the performance of your models on some holdout data in terms of AUC or whatever is your performance measure of choice. As a matter of fact, you would want to use the same algorithm because, you know, some algorithms are able to pick up multicollinearity, others are not. So the way an algorithm judges the importance of a feature varies across algorithms somewhat. And then it makes much sense, I believe, to use, you know, the view of feature importance of the algorithm that you will use later on. And if you assess this algorithm on holdout data, you protect against overfitting in the standard way. As a matter of fact, this is a very good point. I was a bit vague on that. Apologies. When talking about this backward regression trimming, also in the scope of the previous slide with the p-values. Stage-wise regression is very popular. It's very big, and any decent package would have functionality inbuilt. And it's done very often together with proper regression models, linear regression, maybe generalized linear models, or generalized additive models, the GAMs. If these don't make sense to you, not to worry, it's not dramatically important for this course. And indeed, if you pay attention to the p-values and make your decision whether to keep or drop a variable based on the p-values, you have to carry it out in these frameworks, in the linear world, or in the world where you have theoretical distribution of coefficients. You won't have something like that for neural networks or decision trees, and many others, for SVMs for that matter. So you just don't have that. But if you think about this pseudocode here, you can implement that with any algorithm, be it regression in the sense of linear regression or a tree or something else. And if you read closely, choose the overall best model based on validation set performance. You can also examine the value of a single feature with any measure you like. So this is really the pure wrapper approach. There is stage-wise regression analysis, is a bit something in between. It uses the learning algorithm, if that were regression, to select features. So in that regard, it's a wrapper. But normally a wrapper would also judge performance in an out of sample way, as opposed to using a p-value from an in-sample test. So here we have a pure wrapper in all its beauty, but also in all its complexity, computational complexity. Now, I certainly ran almost out of time when reaching the part that cost me by far the most time in preparing the session. Embedded methods. Quickly want to comment on these methods. Many modern algorithms possess inbuilt feature selection capabilities. You tune these methods, and by tuning these methods, they will implicitly select features, or at least avoid a detrimental effect from irrelevant features. These abilities ready many modern algorithms to work with high-dimensional data set. If you tune them properly, if you apply them in a sound way, irrelevant features will not hurt you, although you might not formally select them. And I'm introducing that in the scope of not too complicated models, namely linear models, but those linear models that include penalty term. Regularized regression is the keyword here. We discussed that in the statistical learning chapter. Remember that in regularized regression, the idea is that we penalize models for having many parameters. And in regression, that translates into many variables and large magnitude of beta values, large magnitudes of coefficients. In trees, that would translate into penalizing the depth of the tree somehow. But let's not think about trees for now. What you see here are, let's look at this formula. We have squared residuals here. I use J to denote my loss function. So this is a loss function that depends on a vector of parameters beta, regression setting. And in our loss function, we find the standard term that measures the fit of our model, for example, in terms of the squared residuals of our linear model. And in addition, we have a penalty term where we add the sum of the squared coefficient values to our loss function. And when we then minimize this loss function, our learning algorithm or our solver has an incentive to look for solutions where beta is small in magnitude. And of course also look for solutions where residuals are small in magnitude, but the complexity as measured by beta has an impact on our loss function. And this was the rich penalty because we measure the squared sum of beta, and if we measure the absolute sum of beta, that was the L1 penalty that's used in lasso. And the graph depicts this, how we have beta 1 and beta 2. So first understand the coordinate system. We have beta 1 and beta 2. And we will have some loss function as well. And you see these contours in blue. They depict the value of our loss as a function of beta. And the loss as a function of beta is a squared function. This is why we see these circles or ellipsoids. And the red dot, one of them marks the solution where our loss is the minimal. And then the dashed circles depict certain settings where the squared sum of beta 1 and beta 2 is of some quantity. And then essentially these two factors come together and we see that the optimal solution to our minimization problem changes if we consider this penalty. Normally, you see the OLS solution here, but in the OLS solution, the squared sum of beta 1 and beta 2 would be large. And you also see an alternative solution where you have the sum of squared residuals larger than at the optimal point here right in the center, but where we also see a smaller value of the squared sum of beta. So by penalizing our loss function through adding this complexity, we will typically arrive at a different solution to our optimization problem, different solution of beta, and which solution we arrive in depends on the parameter lambda, which allows us to govern how much overfitting we like. And this is the tuning parameter. And what you can then do is you can analyze how the magnitude of coefficients changes in response to lambda. And yeah, maybe about time too. You can look at the R code later on and recode that yourself. There is a nice package I'm using here, GLMnet. What you can compute is the full regularization path. This is how they call it. You see this analysis, a log of lambda and the magnitude of beta where the colors depict coefficients, different variables. And I'm using the home credit data here. This is hard to read because I have all the features. Let's cook it down. Here I randomly picked a few features that I found interesting. Credit by income, the amount of credit bureau inquiries, yeah, shortly, For a client, the percent worked variable, which is a ratio feature that we developed as part of our feature engineering with this data set. And what you can then analyze here is whether these coefficient values, whether the corresponding coefficient values are different from 0 depending on lambda. And we see here how this is lasso regression, how when we increase lambda from left to right, the values of beta get less and less and less, and how then beta for certain variables becomes 0. And the larger lambda gets, the more variables receive a coefficient of 0, meaning they have been dropped. Beta equal to 0 means effectively the feature has been dropped, has been discarded. So the L1 penalty in lasso really performs feature selection, and then this gives us a nice way to look at the relative importance of different features. The green one here, for example, which is percent worked, turns out as the most important features. It is the last one that the model removes. It also has the largest absolute coefficient value, while the Cyan one, which is the number of credit defaulters in the social network of a credit applicant, this one here would be the second most important one. And where interestingly, variables that I would have imagined to be super strong, like credit by income, turns out to be entirely irrelevant and getting kicked out by our lasso very, very early. This exemplifies embedded feature selection. So no time for summary, but I put some key take-homes. As always, by the way, normally I don't have time for these points, but make sure you read up upon that because I'm really trying to single out the most important takeaways from a chapter. And with this, I want to close the session, and I will actually see you one more time today for the exercises. So for now, let's just close the session and take a little break. Thank you.